Okay, now we consider important topics in matrix algebra, which is the identity matrix. An identity matrix is a square matrix n by n, whose general element we can write is aij n by n, because it's a square matrix, and this general element aij is equal to 1 or to 0 is equal to 1 for each I equal to j, and is equal to 0 for each I other than j. For instance, an identity matrix 3 by 3 is a matrix 1 0 0 0 1 0 0 0 1. So the elements are equal to 0 except the element on the main diagonal, in which I is equal to j, because this is the element a11, this a22, and this is a3. Why is important the identity matrix? Because if we consider a matrix A multiplied by an identity matrix, this is equal to the identity matrix multiplied by matrix A, and we have seen that it's not true in general that A times B is equal to B times A, and this is equal to A. For instance, if we consider we can consider, for instance, matrix A equal to 1 2 3 4 5 6. In this case, if we consider the identity matrix 2 by 2, very simple, 1 0 0 1, it's easy to check, and you can try by yourself. Then we go away, you can check in the lecture that A times I is equal to I times A, and is equal to A. We can check, for instance, if we want to compute a matrix 1 2 3 4 5 6, and we can multiply this matrix by 2 by 2 identity matrix. This operation is possible because the number of columns of the first matrix is 2, and this is equal to the number of rows of the second matrix, and inverse order. We have to delete the blackboard. So we can write again the matrix A 1 2 3 4 5 6, and we can multiply by the identity matrix 2 by 2. It's possible to compute this operation because the number of columns of the first matrix is equal to the number of rows of the second matrix. If we perform this operation, the final results will be a matrix with the number of rows of the first matrix, so 3 rows, and 2 columns, the number of columns of the second matrix. So we can write the elements. In order to compute these elements, we consider the first element, the first row, and the first column. Then we have 1 times 1 plus 2 times 0, which is equal to 1. Then we consider second columns, 1 times 0 plus 2 times 1, which is 2. Then we consider the second row and the first column, 3 times 1 plus 0 times 4, which is 3. 4 times, then we have the second column and the second rows, 4 times 0 plus 4 times 1, which is 4. Finally, we have the third row and the first column, which is 5 times 1 plus 6 times 0, which is 5, and 5 times 0, considering the second column, 5 times 0 and 6 plus 6 times 1, which is 6. So finally we get matrix A. In the same way, you can check by yourself that if we multiply this 2 by 2 identity matrix by matrix A, which is 1, 2, 3, 4, 5, 6, you get matrix A. It's possible to perform this product, yes, because the number of this product is not possible in this case. It's not possible because the number of columns of the first matrix is 2, but the number of rows of the second matrix is 3. So this operation can be computed. But if we consider a square matrix A, in this case we get the relation in both sides. For instance, consider 2 by 2 matrix in order to simplify algebra. So in matrix A, which is equal, I don't know, minus 1, 2, 3, 5, in the identity matrix of the same dimension, 1, 0, 0, 1, you can check by yourself and see. Now you stop the video and then you can continue and check the result. In this case, A times I will be equal to, consider the first row in the first column, minus 1, because it's minus 1 times 1 plus 2 times 0, then first row second column, which gives 2, then we consider second row first column, which gives 3, and again second row second column, which gives 5. In this case you can also compute I times matrix A, because the number of columns of I is 2, and it's equal to the number of rows of A, which is equal to 2, and you can check by yourself, you get minus 1, 2, 3, 5. So in this case we can say that A n by n in general multiplied by I n, which is an identity matrix n by n, is equal to the identity matrix of dimension n multiplied by the matrix A n by n, square matrix A, and this is always equal to A. We say in mathematics that the identity matrix I is the neutral element with respect to the product between two matrices. Okay, we can also define zero matrix as a matrix, given matrix A, and zero matrix is a matrix such that A times 0, where 0 is zero matrix, is equal to 0 plus A, and is equal to the matrix A. In other words, if we have a 2 by 2 matrix, for instance 1, 2, minus 1, 5, we can add a zero matrix of the same dimension, 0, 0, 0, 0, and we get the same matrix A. So 1, 2, minus 1, 5, because we are going to sum the corresponding elements of the matrix A and the zero matrix. It's important to, there is another important properties that we can write. If the product between A and B gives a zero matrix, this doesn't imply that the product between B and the A is equal to the zero matrix. And we can check through an example. Consider a matrix A equal to 3, 9, 1, 3, and the matrix B equal to minus 3, 6, 1, minus 2. If we compute A times B, it's possible to compute this because the number of columns of matrix A is 2 and is equal to the number of rows of the second matrix. If we are going to compute, we get first row, first column, 3 minus 3 plus 9 is equal to 0, and again this is equal to 0. If we do the same with the second row, we get 0 and 0, so we get the 0 matrix. We can write again the matrix. In this case, matrix B equal to minus 3, 6, 1, minus 2, and matrix A equal to 3, 1, 9, 3. B times A is equal to, we take first row, first column, minus 9 plus 6 minus 3, second row, minus 27 plus 18, which is I think minus 9. Then we take second row and first column, so we have 3 minus 2, 1, and then second row, second column, which is 9 minus 6, 3. As you can see, A times B is equal to 0, but B times 1, B times A is other than the 0 matrix. So this is a very important property of 0 matrix and the product between two matrices. A very important topic in matrix algebra is the topic of determinant. Determinant is a scalar associated with a matrix. It's possible to compute a determinant just for square matrix. Now, let's consider a matrix A n by n, so a square matrix. We need to define, in order to compute determinant, the so-called minors of a matrix. Minors of a matrix Mij, which means minors of the element or matrix A of the element Aij, is the determinant, and we have to define what is the determinant, is the determinant of the submatrix we get deleting the row I and the column J in the matrix. So if we consider an n by n matrix, we have n square minors, possible minors. If we understand what is a minors, but we will see better what is a minors with an example of the 2 by 2 matrix, we can consider the so-called cofactor. A cofactor we can write as C cofactor Ij is given by minus 1 to the power of I plus j multiplied by the minors I and Ij, and this is the definition of cofactor. Then we have the Laplace expansion in order to compute the determinant of matrix A, so the scalar associated with matrix A. In this case, this will be equal to the sum for j equal to 1 until n of Aij multiplied by the cofactor Cij. And this also, so in this case we are considering the row I. We can also consider the column if we have the sum of for I equal to 1 until n of Aij. In this case we are considering a column for the cofactor Cij. In order to better understand this definition, consider a 2 by 2 matrix A, general matrix with element A11, A12, A21, A22. In this case, in order to to consider the minors, we have the minors M11, and this is defined as the determinant of the submatrix we get if we delete the row and the column of the element we are considering. So in this case we have A22. And the same way we can get M12, which is equal to A21, because we delete the first row and the second column, and we get A21. Then we have M21, which is equal to A12, and M22, which is equal to A11. In order to get the cofactor, we need to consider the position, the row and the column of each element. So cofactor 1 will be equal to minus 1 to the power 1 plus 1 times M11. So it will be equal to A22. The cofactor C, we have to relate, the cofactor C12 will be equal to minus 1 to the power 1 plus 2 times the minus M12. So this is negative because we consider power of 3, and we have minus A21. In the same way, the cofactor C21 will be equal to minus 1, so C21 to the power of 2 plus 1, so it's the same, to the, which multiplies the minus M21, so will be equal to minus A12. Finally, the cofactor C22 will be equal to minus 1 to the power of 2 plus 2, which multiplies the minus M22, so will be equal to C22 will be equal to A11. At this point we can compute the determinant of matrix A, of this 2 by 2 by matrix A, as the sum of the first element. If we take, for instance, the first row, the first element of first row multiplied by the cofactor this way, C11 plus A12 multiplied by the cofactor C12, so will be equal to A11 times the cofactor of the element C11, which is A22, plus A12, which multiplies the cofactor C12, which is equal to minus A21. So finally we get the well-known formula to compute the determinant of 2 by 2 matrix, which is A11 A22 minus A12 A21. We get the same results if until to take the first row, we take, for instance, the first column.